I welcome everyone to my class today. You are all welcome to my class today. In our last class, we rounded off the topic composition and resolution of coplanar forces. Going further today, we are beginning a new topic called equilibrium. What are our learning objectives for today? At the end of this lesson, students will be able to 1. State the principal conditions of equilibrium of a rigid body. 2. Apply these conditions in solving problems. And the first thing we are going to be looking at is translational equilibrium. If a body remains at rest, under the action of given forces, we say that the body is in a state of equilibrium. Now, I want you to know that a body like this is not moving. Does not mean that there are no forces acting on that body. A body may be at rest and still have forces acting on it. Now, let's look at from Newton's first law. That's this law here. If a force acts on a body, it changes its state of rest or uniform motion. When I apply a force to this body at rest on the screen here, it changes its state of rest or its uniform motion. If it's already moving, it changes its uniform motion. Now note that two kinds of motion are implied in Newton's first law. I believe I'm talking to physics students. You already have a foundation in this topic in your physics class. Okay, two motions are involved in this or are implied in this Newton's first law. That's translational and rotational motion. There are bodies, I'm here now, there are bodies which remain at rest under the action of forces which have tendency to cause translation. I told you before that a body is at rest does not mean there are no forces acting on it. If the forces acting on it have the tendency to cause a translation, that is to cause it to move from one point to another, that's translation. It may not be moving it at the moment. If the body is at rest, there are forces acting on that particular body. But those forces acting on it have the tendency to cause a translation. Now, this state of equilibrium is called what? Translational equilibrium. A body is at rest. There are forces acting on that body, but those forces is not causing it to move. But those forces have the tendency to cause translation. What's translation? That's moving an object from a point to another. That's translation. So that's we'll say in that situation that the body is in translational equilibrium. So let's forge ahead and see what we have on our next slide. And let's look at the conditions of equilibrium. Now you see the objects I have on the screen here. The object I have on the screen, that's this. That's like a block resting on a table. That's a block resting on the table. There are 4 forces: an upward force, there's a downward force acting on it, there is force F1, another force acting on it to my right, and there's another one acting on that object to my left. So there are 4 forces acting on that block that is resting on the table represented in this diagram. Now, if the magnitude of F1 and F2 are equal, then I'm reading here, I'm explaining that particular place I mark now. Then two forces balance each other. The block therefore remain in translational equilibrium. Now, if this force and this force are the same, that means the block will not move from the position. Is still in translational equilibrium. Good. We have established what we call translational equilibrium. Now let's check the conditions. Remember in our diagram that we saw in the last slide, there is a force acting to my left. There's another one acting to my right, acting on that particular box or the block resting on the table. Now, if those forces are this F2, this one was F1. Remember the diagram? Good. Now, because this direction is this way, we consider it as negative and we consider this as positive. Remember, it says if their magnitude are equal. So if F1 is equal to F2, this negative we are seeing here is only indicating the direction of the force, that the forces are in opposite direction, but their magnitude are the same. The negative you are seeing that I circled there indicates that the forces is acting in an opposite direction to F1. Good. So if I collect the terms together, if I bring minus F2 here, I have just that simple equation, F1 plus F2 equals to 0. Good. So it means the sum of horizontal components of the forces is equal to 0. I have the horizontal component, two forces there, F1 and F2. So that equation that I mark here is showing that is equal to what? 0. Now let's look at the upward force, which we call N, and the downward force, which we call mg. Now the same thing, this mg is considered as negative because it's going opposite direction to N. So once you see two forces acting in opposite direction, the other one is considered as negative. This is negative. Obviously, if you look at your Cartesian plane, this side is negative. So we can take this as what? As having a negative sign, showing that it is going in opposite direction to this force N. Good. Now let's go further. In general, okay, before I get to that, it means the sum of the vertical component of forces is also equal to 0. So if I bring this one, if I bring what I have here together, if I bring this one to my left, it gives me this equation. It becomes positive. It means sum of the vertical component of forces is also equal to 0. The sum of the horizontal equal to 0. Sum of the vertical component of forces also equal to 0. So it means so this is what stands. This is the condition that we need now to tackle our problems. In general, if I have this is what we should bear in mind for all the solution we are going to be doing for today's class. Those are the conditions of what? Equilibrium. Okay, summation of all the forces. The x represents horizontal. Summation of all the forces along the horizontal is equal to 0. Summation of all the forces along the vertical is expected to be equal to 0 for an object in translational equilibrium. For an object in equilibrium, then the resultant will also be 0. Of course, remember we taught ourselves, or you were taught when you have force y, force x, we did this under resolution of forces, and you have a resultant. If this is 0, this is 0, what will be your resultant? It will also be equal to 0, and that's why we have this here. Okay, So we have those things to be equal to 0. Our resultant is equal to 0 for an object in equilibrium. The summation of the forces along the horizontal is also equal to 0. The summation of the forces along the vertical is also equal to 0. Fine. Let's forge ahead in this class today. So I've defined all your summation f of x, summation f of y, and I've defined my summation r. So we've seen the condition now that is necessary. Now let's take the first example. Let's take our first example. An object P of mass 5 kg is suspended. Of mass 5 kg is suspended. We are looking at this particular question now. By means of two light inextensible strings AP and BP. The strings AP and BP make respectively angles of 30 degrees and 60 degrees with the downward vertical. The magnitude of the tensions in AP and BP are respectively T1 and T2. Okay, so we are given tensions in the AP and BP to be T1 and T2. The question they are asking us first is expressed as vectors in component form, all the forces acting on P. All the forces acting on P. Now, we're going to take it one by one. Remember, you are told, you were taught in vector. We can also write a vector like this. If I have a vector xi plus yj, we can also write it this way. Remember, x and y. Vector can also as well be written this way, either like this or like this. Okay, so we are going to be using this particular one now. Okay, expressed as vectors in component form, all the forces acting on P. So there are forces acting on P. Now let's look at those forces in our next slide. Let's see the diagram that follows. Good. So this is a sketch to that. We are told that an object P. So this is our object P. Let me show us with my pen. My object P is here. Okay, of mass 5 kg. That's why you see this mass. The mass is 5. Okay, 5 kg. That's supposed to be 5 kg, kilogram. Should be kilogram, 5 kilogram. Good. The weight is 5 kg. And if you look at the question, we are given our G to be equals to 9.8 meter per second square. So if I multiply mg 9.8 times 5, it gives me 49 newtons. Good. Okay, so there are tensions AP. Remember they mentioned AP. There are strings AP. This is the string AP and another string BP. So of course you know that there is a tension force on that AP, which we call T1, and there's another tension on that BP, which I've called T2, as you can see on the screen. Good. The magnitude of the tensions in AP and BP are respectively T1 and T2. So we have been told T1 and T2. That's already represented on the diagram. Good. Expressed as vectors in component form, all forces acting on P. All forces acting on P. How many forces are acting on P? There is T1 and there is T2. Only two forces. Two forces. They say all forces acting on P. There are two forces on P. So that's what we want to do now. Okay? The forces acting on P are, three forces acting on P, the point P. Remember that weight is also a force. This weight is a force. There's a tension T1. There's a tension T2. There are three forces acting on that point P. There's an object at this point, at that point, that's middle there, okay? So three forces are acting on P. Now let's resolve all the forces to our vertical component and horizontal component. Now, as seen in the diagram, we are told that AP and BP make 30 and 60 degrees with the downward vertical. This is the 30 degrees. Downward vertical, that's AP makes. Then BP makes 60 degrees. That's why I use this broken line you are seeing here. There's another broken line you are seeing there. That's the 60. They said the 30 and 60 are made with a downward vertical. That's why I've circled 30 degrees and 60 degrees. Good. Now, at this center point, if we make a construction there, somehow, a construction there, it means here is going to be 30 degrees and this other part is going to be 60 degrees. Good. So here will now be, to get the angle, you remove this 30 from 90. So I have this 60. You remove, to get this angle here, let me clear my screen so that I can explain better again. To get this particular angle here, since inside here was already, this inside was already 60. If I remove that 60 from 90, I have this 30. That's talking about this angle here, that angle. Good. So I have 30 degrees against the horizontal line, and that is what we are going to use to do our resolution. Okay, so just as at that point, we have something like this here. There's a force 30 degrees here, and there's another force here 60 degrees. I'm trying to make you see the diagram. Okay, that's, we want to use this 60 and 30 degrees to resolve the forces T1 and T2. Good. Remember what we did, resolution of forces. We talk about that, isn't it? Now, this force now, if I want to resolve this force and I want to resolve this force, as you can see on the diagram, I want to resolve T1. Let's pick them one after the other. If I resolve this T1, okay, to the horizontal this way, that means it's going to be negative, isn't it? My Cartesian plane, this side is negative. That's why you have this negative here, negative. Okay, and that's why I have minus t cos theta. Okay, remember this, where I'm resolving to here is what my adjacent. Okay, and T1 is your what? Hypotenuse. That is why we have minus T1 cos theta. Okay, now if you look at this, the same T1, I want to resolve it to my vertical. What do I have? If this is the vertical, that's opposite and hypotenuse. That's why we have, I'm resolving to the vertical and this is positive. Okay, that's why I have this one, T1 sine 60 degrees. Good. So I've resolved that T1 using this form of vector. Remember, we can write a vector like this. Of course, force is a vector. Good. So I can write it this way. And the same thing if I also resolve my T2 using these 30 degrees that I have here. Okay, so I'm going to have T2 cos 30 degrees. That's for the horizontal. Horizontal is at the top. Horizontal is this, and this is vertical. Okay, T2 cos theta, and I have T2 sin theta. So if I simplify all of that, here cos 60 degrees is 0.5. So with that negative, I have this. Here, sin 60 degrees is 0.8660 times the T1, I have this. So the same thing, if I simplify this, if I simplify my T2, I have this. Now, resolving my W, of course, we can see that this, my W, is just on the vertical. It doesn't have anything on the horizontal. So, of course, that's why this one is 0. That's why this is 0. Then my 49 that I have there, because it's towards the negative axis, look at it. This W is going down. That's negative. That's why we have minus, we added minus 49. Don't forget that minus is as a result of the direction of the force. So we have along the x-axis, W does not have effect. That's why you have 0. Along the horizontal axis, W has no effect. That's 0. Then along the y-axis, that's why we have minus 49. Let's go further. Now let's look at the very first example. No, sorry, the number 2. The question we just finished answering now is the Roman figure 1 of the question that we have there. Now the Roman figure 2 is telling us that we should write down a vector equation connecting all the forces in one. Remember, we have 3 forces. We have T1, we have T2, and we have a W. Okay, those are the 3 forces. So write down a vector equation connecting all the forces. So we are simply going to apply the law we have learned. Okay, all the forces we have, since they are all in equilibrium, keeping the object at rest in translational equilibrium. So we have T1 plus T2 plus W, everything will be equal to 0. That's the forces, all the forces, summing all the forces together will be what? 0. Okay, good. T1 T plus T2 plus W is equal to 0. So we are already applying the condition we stated. Now our T1, from the last slide we got this. Our T2 we got this for our horizontal and vertical. Then for our W we got this. So we are adding everything now. This is T1, T2, and W. Good. So adding them component wise, the minus this plus the one at the top plus 0. Okay, you see that add all the horizontal components together, add all the vertical components at the bottom together. All these ones, they are at the bottom. Okay, those are our vertical components. Add them together, equal to 0. Okay, so it's going to lead us to solving what we call simultaneous equation. I'm breaking down. Look at it. I'm not breaking. I've gotten my answer for Roman figure 2. That's the vector equation connecting all the forces. That's this one. That's where I have ticked now. Then the question 3 says use the vector equation in 2 to calculate the values of T1 and T2. The vector equation in 2. So using this place I've ticked now, what the result I just obtained now to solve T1 and T2. So what are the equations I can bring out there? I can have 2 equations. Look at the horizontal components. This one. And that's what I have here, equal to 0. This is equal to 0. Then the one at the bottom for the vertical components, I have where I have that 49, and that is also equal to this same 0, and that's what I have as my equation 2. I have broken it down now. So using what we are simply doing now, we want to solve the 2 equations 1 and 2 simultaneously using simultaneous equation. Of course, we are all used to that. Good. So let's quickly see. Now I want to start from equation 1. If I make T1 subject of the formula there, this is what I have. Okay, good. Now if I simplify, punch my calculator I'm going to have that 1.732 T2. That's what I have. So I make that my equation 3. So let's substituting the value of T1 in 3 into 2. Okay, I will substitute that T1 into equation 2 in my next slide now. Good. Let's quickly see that and let's round off this particular example 1. This is the Roman figure 3 solution we're about to obtain. So substituting this now, substituting T1, the T1 we obtain into equation 2. Remember, this is that equation 2 from the last slide. The only thing we are doing is we are substituting T1. T1 was here, remember? So that's why we are putting that value of T1. T1 was 1.732 T2. That's how you see this replacing that. Okay, plus 0.5 T2 minus 49. So just simplify. Open the bracket here. Open the bracket. So if you simplify and add up, you get this equation. So making T2 subject of the formula, as you can see, if I bring 49, it becomes positive 49 over 2. So I have my T2. Okay, so to now obtain my T1, we just go back to this formula and substitute your T2. So that's 1.732 times 24.5. That gives me my T1. So I've succeeded to get both T1 and my T2. Good. We've finished solving the first example. I hope it's crystal clear to every one of us. Good. So we've gotten our tensions T1 and tension T2. Okay, good. Let's move to the next slide. Let's move to the next slide and see the next example that we have. Good. The second example is street lamp of mass 10 kg is suspended at a position O. Is suspended at position O by 2 wires OP. You can see it in the diagram. I sketch my diagram looking at the question. This diagram was sketched by me. That's my sketch. This is the question. You sketch the diagram yourself. A street lamp of mass 10 kg. So just use an arrow so as if my object is what we have at the center there. So weight is the downward force. You remember in your physics, that's why in the last question we brought it down to weight is a what? W is what? Downward force, a force acting downward. That's why the W is here. Good. And this time around we are giving our G as 10. Remember that W is equal to what? Mg. Physics, you remember. So if you multiply your M times 10, because G is 10, that's 10 times 10, that's why we have 100 newtons. I have my 100 newtons there. That's for my W. Okay, now let's look at the question further. It's suspended at a position O. That's this O you see here. Okay, by 2 wires. By 2 wires. OP and OQ across a road such that each wire is inclined at an angle 80 degrees to the upward vertical. Look at it. I interpreted that here. Upward vertical. That's vertical. 80 degrees. 80 degrees. And that's the same thing we have here. 80 degrees. 80 degrees. Okay. So OP and OQ across a road such that each wire is inclined at an angle 80 degrees. So that's why we have the 280 degrees there. Now, if the system is in equilibrium, you see, they are telling us the system is in what? Equilibrium. The object or the lamp is at rest at point O. And they said it's in equilibrium. It's in equilibrium. That's translational equilibrium. So we're going to apply the same thing we establish in our condition. Summation f of x is equal to 0. Summation f of y is equal to 0. Then our resultant will also be equal to 0. That was what we established as condition for solving this particular question. Good. Now, if the system is in equilibrium, calculate the tension in one of the wires. And if you are smart, let me quickly show you something. If you are very smart, you will know that this looks like a what we call isosceles triangle. Why? Because altogether here I have an angle 160 degrees. That angle is 160 degrees. That's adding 80 and 80, 160 degrees. Okay, now if you look at here, this angle 10 here will also be equal to 10 here. Why? Will also be equal to 10 there, isn't it? Why? Because they are alternate angles. What? Alternate angles. The same thing here will also be equal to 10 degrees. Okay, so it means if here is 10, here is 10, that means I have an isosceles. It looks like an isosceles, not it looks like, it is an isosceles triangle. Isosceles triangle. So obviously it means the tension here and the tension here, the two tensions, they will be equal. Just the same way two sides of isosceles triangles are equal, these two tensions are expected to be what? To be equal. The two tensions should be equal. Does that make sense? Good. If it makes sense to you, it means I'm trying to relate it with this isosceles triangle so that you know that the two forces are expected to be equal. That's why the question is telling you that you find the tension in one of the two wires because they're expected to be the same. So obviously we shouldn't expect more than this. The tensions are the same, and I'm showing you from the triangle. Okay, the tensions are what? They are the same. Good. So let's go further and solve our question as we round up for this class after this particular example. Good. Good. Let's look at that. Let T2 equals to T1 equals to T. I'm trying to show you from what I've established in my last slide using isosceles triangle, we know that the two are equal. Okay, what will be the summation of my f of x? Summation of my f of x. Now if you look at it, my f of x, if I resolve to the two forces, to my vertical, okay, when we resolve T1 and T2, I have T cos 10. Remember, I have a force like this, something like this, there's a 10 degrees here, there's a T1, this 10, there's a T1 here, there's a T2 here. Good. So if I resolve to my horizontal, these two, this way and this way, this one will be negative. That's this T minus T cos 10. Here will be T cos 10. Can we see that? And that's why we have this on the horizontal, resolving the two forces along the horizontal. Does that make sense? Okay. Remember, this negative you see here is because of the direction. If I'm resolving this force towards the left hand side of the horizontal axis you see there, that's why we have the negative. Good. Of course, we have established that summation f of x is equal to 0 if an object is in equilibrium. That's why we have that. Then summation f of y2, f of y is also expected to be equal to 0. That means all the forces along the y-axis will also be equal to 0. Now let's resolve the other one. This one too is also 10. Okay, 10 degrees there. That's we have we want to resolve to my vertical now. Okay, it will give us the same thing, t sine theta plus t sine 10 degrees, and also t sine 10 degrees. Okay, so I will now have those forces on my vertical. So if I have those forces, remember I have it, this is W, Remember the W is 100. The W is what? 100. We got 100 before. Do you remember? Why we multiplied 10 times 10? Because my mass, the mass of that object is given as 10 kg. So we have 100 newtons. Why? Because this is a downward force for W. There's a downward force for W. So that's why we have a minus 100 there. So T sine 10 and T sine 10 will give us 2 sine 10 degrees. The minus 100. So all the forces along the vertical, I have a W and I've resolved the 2 here. So then I have the 2 tension. Okay, so we add up and we say we equate it to 0. That's why I'm equating to 0 here. Okay, I'm equating to 0. So if we solve now, solving this equation, if I solve that, my 100 comes and becomes positive here. So making T subject of the formula, that's 100 divided by 2 sine 10. Okay, of course, these two cancels out 100, so I have this. So if I divide, punch your calculator, if you divide 50 divided by sine 10 degrees, I'm going to have 287.9 newtons. I've gotten the tension force, one of the tension force, as the question has required. Calculate the tension in one of the two wires, and that's the tension in one of the two wires. So I've done justice to the question. I believe it was clear. Okay, I expect you to listen to this video over and over for you to really gain mastery of these two examples. With these two examples, there is no question you will see that you will not be able to tackle. Just follow my the two examples closely and with rapt attention. Watch the video over and over again, and you'll see that we have done something that really makes sense today. Now let's quickly summarize. Of course, we all know the summary. We only mentioned 3 things. We talked about resultant, summation f of x, summation f of y. All of them are expected to be equal to 0, as you can see. Okay, obviously, you know, when you resolve a force, when all forces along the vertical, f of x, summation f of x, if is equal to 0, summation f of y is also equal to 0, what do you expect the resultant to be? Resultant will also be 0. That's for a force, or for forces acting on an object in equilibrium. So when you resolve each of the forces along the x-axis, the summation gives us 0. When you resolve the force acting on a body, all, oh sorry, this is supposed to be y, here is x, sorry. Okay, that's y, and here is x, that's my x-axis. Good. So the summation of f of y will also be equal to 0. Summation of f of x will also be equal to 0. And if the two are equal to 0, my resultant will be equal to 0. Good. I believe we have done something very nice and tangible in this class. We're going to be seeing in our period 2 later this week on Thursday, and I want you to expect our weekly quiz on Thursday. Please go over this video over and over, so I believe you can feel me teaching you live. God bless you till we meet again. Thank you so much. All right.